I come alive when the sun goes down. I come alive when the moon comes down. I come alive when the sun goes down. I come alive when the moon comes down.
Alright, sound check. Alright, now this time, without any interruption from the audience, unknown capacitor. In part 1 of this series, we looked at using series resonance between a known inductor and an unknown capacitor to work out the value of that capacitor, and that was done by transposing the equation 1 on 2 pi root LC. A little bit difficult for some people to do that, and if you don't have a known inductor, well, it's impossible to do that. So now we go on to part B, which is using the time constant method. And in this time constant method, we have the exponential voltage rise across a capacitor in an RC circuit. And we know that there's 5 time constants taken to charge that capacitor fully. And the first time constant is 63.8% of the total supply voltage. So we're going to be putting a square waveform into our RC circuit, and then we'll use the oscilloscope to measure the 63.8%, and then we'll drop down and we'll measure how many divisions along horizontally that represents on the oscilloscope, convert that to time, and then we'll have the time for one time constant. Once we know that, with a 10K resistor, we can do some really simple maths and we can come up with the value of the capacitor. I've actually got the oscilloscope connected at 2 points, so I've got the exponential waveform across the capacitor shown here, but I also have another oscilloscope probe connected to the input of the circuit, so I'm seeing that square waveform. Here's the oscilloscope set up in front of me now. There were 2 different ways to do this. I could have used the roll function and then stopped it rolling when I got to the exact percentage I wanted. But in this case, I've just used static functionality of the oscilloscope to display that exponential waveform against the step voltage that I'm putting in. And I've got 1 volt per division. I've got 1, 2, 3, 4, 5 divisions of step input, so 5 volts. I have to find 63.8% of 5 volts and then drop down. I've got another sheet prepared here. So like it says on my little cheat sheet, 63.8% equals 1 time constant. So step 1, I need to find that percentage of the Vmax. And then step 2, I have to drop down vertically and measure the time between the beginning of the rise and where and to the point where it got to 63.8%. And then I can transpose this formula, which is really simple, where it's torr equals CR, that is 1 time constant equals CR. It'll be C equals torr on R. And then we did this using the 10K ohm resistor. 10K ohm resistor I had in my circuit, and using the first capacitor again on my unknown capacitor panel, it worked out that we got 0.01 microfarad of capacitance. Just looking at my notes, it worked out we had 100 microseconds to reach the point of 63.8% of Vmax. We had a 10K ohm resistor, so dividing 100 microseconds by 10,000 gave me 0.01 microfarads, and that's ideal because we did work out in part 1 that we had I worked out I had 9.2 nanofarads compared to 10 nanofarads, so the 2 results are extremely close. Alright, so that is the unknown C using the time constant method with the oscilloscope and a resistor and a capacitor. This has been Greg Moore for New South Wales TAFE.
I come alive when the moon comes down. I come alive when the sun goes down.